In this video, we are going to talk about some properties of colloids. The very first property that we are going to discuss is colligative properties. Colligative properties like osmotic pressure, relative lowering in vapor pressure, depression in freezing point, and elevation in boiling point, which are shown by true solutions, are also shown by colloidal solutions, but the only difference is that the values are of smaller order for colloids as compared to that for true solutions. This is because if we compare the same concentration of a true solution with that of a colloidal solution, then the number of particles present in a given volume of a colloid will be less as compared to a true solution. This is again because colloidal particles are larger in size than the true solution particles. Another significant property shown by colloids which is not shown by true solution is Tyndall effect. John Tyndall, a physicist, studied this property in detail, and so to honor him we call this property as Tyndall effect. This property is shown by colloids by virtue of their behavior to scatter light in all directions. As a result of scattering of light, the path of the beam of light which is passing through the colloidal solution becomes illuminated, and this is known as Tyndall effect. In order that a colloidal solution shows this effect, the particles of the colloid should satisfy the following two conditions. First of all, the diameter of the particles should be nearly of the same order as that of the wavelength of the light which is allowed to pass through the solution. And secondly, the refractive indices of the disperse phase particles and dispersion medium particles should differ greatly in magnitude. Now this figure clearly indicates or shows the Tyndall effect in the two types of solutions, that is true solution and colloidal solution. The beaker containing a milky solution contains a colloid, and the other beaker which has a clear transparent solution contains a true solution. As is very clearly visible, the path of the beam of light which is allowed to pass through these two beakers is visible in the colloidal solution, but it is not visible in true solution. So this is because of the Tyndall effect shown by colloids which is not shown by true solution. Hence Tyndall effect can be used as a property to distinguish between true solution and a colloidal solution. Another important property of colloids is Brownian movement. It is the continuous random zigzag motion by which the colloidal particles are moving in the dispersion medium, and while they move in this zigzag fashion, they keep on continuously bombarding with the particles of the dispersion medium. This results into a stirring effect and does not allow the particles of the dispersed phase to settle down under the force of gravity. This property is responsible for the stability of the colloidal salts. Charge on colloidal particles is another significant property which is shown by all colloids. All types of colloids carry either a positive or a negative charge, and the charge on colloidal particles arises due to preferential adsorption of either positive ions or negative ions from the dispersion medium, which means that the positive or negative ions which are present in dispersion medium and which are in common to the ions present in the colloidal particles are preferentially adsorbed on the surface of colloids, and that results into development of either positive or negative charge on the colloidal particles. This can be clearly understood by taking an example, the preparation of silver iodide salt. In the first case, as is clearly visible in the figure, excess of potassium iodide solution is taken and into it silver nitrate solution is added slowly, dropwise. The reaction between silver nitrate and potassium iodide will result into the formation of silver iodide, which will be present as a colloidal particle in the dispersion medium. Now, since potassium iodide is taken in excess, so iodide ions, which are in common with the ion present in silver iodide, that is the iodide ion, will be preferentially adsorbed on the surface of silver iodide particles. And because iodide ions carry negative charge, so the colloidal particles will become negatively charged and the resultant sol will be a negatively charged sol. Whereas in the second case, silver nitrate solution is taken in excess and into it we are adding potassium iodide solution dropwise. Again, reaction between silver nitrate and potassium iodide will result in formation of silver iodide colloidal particles, but this time silver ions, which are in common with the ions present in the colloidal particles, are in excess in the dispersion medium, and hence silver ions will be preferentially adsorbed on the surface of silver iodide particles. Since silver ions are positively charged, so the colloidal particles will acquire positive charge and the resultant sol will be a positively charged sol, as is very clear from the diagram shown here. First case results into a negatively charged sol and the second case results into positively charged sol. Now, all the colloidal particles in a colloidal solution carry same charge, and presence of this equal and same charges on the colloidal particles will result in repulsive forces between them, due to which they will not aggregate, and since they are not aggregating, they will remain in the colloidal state and not change into a precipitate. That is, colloidal solution will not change into a suspension and hence the stability of the sol will be maintained. So, charge present on colloidal particle is also responsible for the stability of these colloidal solutions. Now, once a layer of either positive or negative ions gets adhered or adsorbed on the surface of the colloidal particle, another layer of oppositely charged ions known as counter ions is also created around the colloidal particles. So, the layer which is of the ions adsorbed on the surface of the colloidal particle is known as the fixed layer, and the second layer which develops around it is known as the mobile layer because it consists of ions which are free to move around in the dispersion medium. Now, this can also be seen by another example of ferric hydroxide sol, wherein the ferric hydroxide colloidal particles are surrounded by positively charged ferric ions which constitute the fixed layer of the adsorbed particles, and a second layer of chloride ions, the negatively charged ions, which were present in the dispersion medium, is formed as the mobile layer around this fixed layer of charges. So, combination of two layers of opposite charges is created around each colloidal particle, and this combination of two layers of opposite charges is known as Helmholtz electrical double layer. The first layer of which is firmly held, whereas the second layer, which is the mobile layer, is the diffused layer of charges present around the fixed layer, and since whenever there is a separation of charge, it results into a difference in potential being created at that particular point. So here in this case also, since there is a separation of charges, one of the fixed layer and the second of the diffuse layer, it results in potential difference between these two layers, and this potential difference created around the colloidal particle is known as electrokinetic potential or zeta potential. Now the next property which is shown by colloids is known as electrophoresis. Now this property also provides a proof that colloidal particles are charged particles, because when we apply electric potential across two electrodes which are dipping in a colloidal solution, then the colloidal particles show a tendency to move towards either of the two electrodes. If they are positively charged particles, they will migrate towards negative electrode, and if they are negatively charged particles, they will migrate towards the positive electrode. And this movement of colloidal particles under the influence of an applied electric potential is known as electrophoresis. As is clear from this diagram, anode is the negative electrode and cathode is the positive electrode, and the salt taken in this apparatus is a negatively charged colloidal solution. On applying an electric potential across this colloidal solution, the negatively charged colloidal particles start migrating towards cathode, which is the positive electrode, and this phenomena is known as electrophoresis. This can also be used to detect the charge present in the colloidal particles, whether they are positively charged or negatively charged. Means we can carry out electrophoresis by putting the colloidal solution in this apparatus, and on applying electric potential across the solution, if the particles migrate towards cathode, then they are negatively charged. If they migrate towards anode, then they are positively charged colloidal solution. Now if we can prevent somehow the movement of the colloidal particles, that is the dispersed phase particles, then it is observed that the dispersion medium begins to move in the opposite direction, and this phenomena is termed as electroosmosis.